Welcome to this video, the 10th video in my series of videos on Georg Cantor's 1895 and 1897 articles on the theory of aggregates and transfinite numbers. Section 10 is titled The Fundamental Series Contained in a Transfinite Ordered Aggregate. On page 129 we see the definitions of ascending and descending fundamental series. These present no difficulties. The notation star alpha is introduced in section 7. The type star omega was used in section 7 as well. Note that fundamental series in M are effectively partial aggregates of M, which inherit the simple ordering defined on M. Hence the notation used to represent a fundamental series, which clearly resembles the notation used to represent aggregates, introduced in section 1. For coherent ascending fundamental series, we see that for each element of one of the series, there are elements of the second that are of greater rank than it. Clearly, we require that the elements of each of the series can be compared, which means that the two fundamental series must be derived from the same aggregate. That is, all of the elements of the fundamental series A nu and all of the elements of the fundamental series A primed nu must be from the same aggregate. Similar ideas apply to coherent descending fundamental series, that for each element of one of the series there are elements of the second series of lesser rank than it. Again, the elements of both series must be taken from the same aggregate. Theorem A says that coherence of series is a transitive relation. Clearly, we must have that coherence is also a reflexive and symmetric relation between fundamental series. An aggregate may have several principal elements since the aggregate may contain several non-coherent fundamental series, each of which have their respective limiting elements in M. Theorem C clarifies that on the assumption that a fundamental series has its limiting element in M, then any second coherent fundamental series must also have the same limiting element. There's nothing to say that a fundamental series will have a limiting element. It may be the case that even though a fundamental series does not have a limiting element in M, that there is another aggregate which would seem to contain an element which could naturally be thought of as the limiting element. There is a problem with this though, since an element that lies in an aggregate other than M would somehow need to have a suitable order defined so that the particular element was somehow compatible, let's say, with the elements of M. This may require expanding the aggregate M to include the new elements, for example. I'll just run through a proof of Theorem C for increasing fundamental series as an example, and to give an idea of how the proofs of some of the other theorems in this section may proceed, since Cantor doesn't give any proofs of the theorems in this section. Theorem D confirms that two fundamental series which have the same limiting element must be coherent. Some of the details of the proof are shown on the screen for the case of two coherent series proceeding in opposite directions. The other cases are not any more difficult to prove. There's no reason at all why two fundamental series shouldn't be coherent, even if they each have no limiting element. Of course, if the series are in fact coherent, then it cannot be the case that one of them has a limiting element and the other no limiting element. Theorems E, F and G don't really require any explanation. There is a distinction to be made between an aggregate which is described as dense in itself and an aggregate which is described as being everywhere dense. The term everywhere dense first appears on page 123, and an aggregate M is everywhere dense when between any two terms of M there are other terms of M. An aggregate N, which is dense in itself, means that every element of N is a principal element. That is, each element is a limiting element of some fundamental series. An aggregate P, which is said to be closed, means that every fundamental series in P has a limiting element in P. This does not imply that every element of P is a limiting element of a fundamental series in P. That is, not every element need be a principal element. That an aggregate may be described using one of the above predicates does not exclude the possibility that the other predicates may also apply to the aggregate. For example, it's possible to have an aggregate which is both dense in itself and closed, but it's also possible to have an aggregate which is dense in itself and not closed. An aggregate which is both dense in itself and closed is called a perfect aggregate. And we see on page 133 that the terms dense in itself, closed and so on can be applied directly to ordinal types. Thank you for watching. If you found this video useful, then please hit the like button and subscribe to my channel. You can see more videos on various topics on my channel, and if you have any suggestions for topics for future videos, then please feel free to let me know and I'll try my best to put something together. Don't forget to hit that subscribe button and keep an eye out for new videos being uploaded to my channel.